Yeah, you have your BA, like you're finishing it up, right?
Yeah, but it's in computer science and we had not that much math. So
Oh, yeah, makes sense,
this is the
makes sense.
problem for me, I'd say.
So, like, after your BA, if you don't mind me asking, like, are you going to go for grad school or, like, what are your plans?
No, I'm just working.
Okay,
It's,
yeah. You work
yeah.
as, like, a programmer? Yeah.
No, penetration testing.
Ah,
Yeah.
penetration testing. Okay,
Yeah.
that's
Yeah.
nice. Uh-huh. Calvin, do you want to talk about, like, how much time it took you?
I was gonna say,
Mm-hmm.
since I already started this course like a bit earlier, I thought B set zero was gonna be like very quick, but I didn't spend too much time on it. But like for example, like for number three, when we're supposed to apply like the formula for cosine of a minus b
Mm-hmm.
to the identity to obtain the addition formula for sine a plus b, like first I got like, oh, like when I extended cosine of pi over 2 minus theta out, like it just ended up sine theta equals sine theta. And I was like, where's the addition formula coming from? Like I think basically the problem set it was uh, harder than expected. Like for example, yeah, and like for like solving under transcendental functions, um, I thought solving for t. Oh, like I thought initially, I thought this was just algebra, and then like somewhere in the middle, like I would get stuck. So
Mm-hmm.
yeah, like deceptively harder, I guess. That's my conclusion.
Right, right. Looks easy,
Yeah.
but
If I
yeah.
like probably sit
Mm-hmm.
down for like longer, maybe like and thought about it, I think I would be able to solve it. But like I have to kind of make a decision of like, okay, how much time do I spend this, and like what can I gain? So I figured I'll come to the lecture stream instead.
Right, right, right.
Yeah, I would totally agree. And it's like, to give an estimation, it's like 1 hour that I spent on it. Because some things you just rush through because you know it, and the others, yeah, not. So,
Mm-hmm.
yeah, like an hour maybe.
Okay. Yeah, Siddharth also sent his solutions. I haven't checked anyone's solutions actually, but yeah, do you want to talk about like what it was for you, Siddharth?
Although I could solve most of, but the function I could not solve the function one and the binomial theorem section, I think,
Okay.
and it took about nearly 1 hour.
Mm-hmm. Mm-hmm.
So I think I need to review that.
Mm-hmm. Mm-hmm. I see.
Did we need to send it to you? I'm sorry.
Yeah, yeah.
I've got it on paper.
You can just send the photos. Most people have sent me photos too. Yes.
Okay. Still okay. Let me see how.
Mm-hmm. Mm-hmm. Okay, did anyone try the complex number stuff? That is actually optional. I'm not sure if anyone tried. Yeah, we decided that
I
we'll
didn't
just.
try,
Sorry?
but I think I have an idea how to do it, but I didn't have enough time.
Makes sense.
I tried it, but I couldn't work it out. Yeah.
Okay, let me download what everyone sent. Um, Ah, Michael has amazing solutions that look very good. Okay. We'll see them. I had the other one, wait. Yeah. Cool. Kelvin, you're also posting your solutions? Yeah, okay, you did.
Yeah, I sent them in the private set.
Right.
And a lot is unfinished where I didn't know how to continue. So
Okay.
yeah.
Hoji, do you have like a set of solutions that you would like to submit? You have.
Not for this piece set, no, sorry.
Okay. So you just tried it, right?
Well, I just tried number 10 since you just mentioned it.
Okay. Okay, let's see. So we have Kelvin's solutions, we have Siddharth's and Michael's. Okay, continue. I'll keep them here because that will be easier to access. Okay. So we have 3 submissions and we'll see where we can go with this. There are in total 8 problems that you need to do. The other 2 are optional. So, which problems is everyone totally comfortable with? Like, doesn't need something to be discussed. Like, they're totally fine with like their answers, submissions.
Third one and fourth, trigonometry.
Okay, so trigonometry section, you're totally fine with it.
And here's a transcendental function.
Okay.
The first one.
The first one?
Yeah, let me see. The 2 questions are so explaining why what a function is essentially, and graphing piecewise functions, I guess.
Yeah, you're
I
cool
already
with
see a
that?
mistake. I think so.
Okay,
I mean,
yeah.
I noticed. Yeah.
Mhm.
Yeah. And the
Um,
rest can be better. Yeah, definitely. Improvement
okay.
is needed.
Yeah, I just asked it so that, like, we can spend like first our time on things that are not entirely clear and then go on to other areas. So, looks like to me, the functions part, there's nothing to talk about, but let's see the submissions.
I could not solve the functions one.
You said you could not solve it?
Yes.
Okay, so
That.
you would like it to be discussed?
Yes, I would like to discuss the first one.
Okay, yeah. I thought it was, okay, yeah. Okay, you said you were cool with trigonometry and transcendental functions, right? Right. Okay. Let's see. Okay, so the first problem says that if you have a curve is symmetric about the x-axis, the point xy must lie on the curve if and only if the point x comma minus y lies on the curve. Now, I'm not sure how many people here are familiar with statements that have if and only if in them. Do you guys know like what to think about when you have something like if and only if, or what it means?
Does it
Yeah.
apply both direction?
I know that it's written as IFF, right? That's the only thing I know. Is it just, it must be hold up.
I think it's equivalence, right?
Yeah, it's implication in both the directions, so that gives you equivalence. So when you have something like if and only if, the way to go about proving something like that is that you prove that in both the direction the implication holds. So in here you have to show that if your curve is symmetric about the x-axis, the point xy lies in the curve. If it lies in the curve, then that implies x comma minus y also lies in the curve. And then you have the other direction too, where if your x minus y lies in the curve, then that implies x comma y also lies in the curve. So that's the bi-direction. In the both directions you have the implication. So so that's the first part of the problem. Then the other part is you have to explain why a curve that is symmetric about the x-axis is not the graph of a function unless the function is y equal to 0. Why it cannot be a well-defined graph of a function.
Yeah, for that, I explained that a function needs to map from from the domain to the codomain, so from x to y. That from the domain there should be like map to one element in the codomain in order to satisfy like a function definition. And multiple elements from the domain can map to the same element in a codomain, but one element, but it cannot map to like multiple elements from the same domain.
Right. That's the definition of a function, and you have to apply that here. But you have to also graphically understand what that means, the definition implies, right?
Yeah, like the vertical line test. If you draw a line and it crosses 2 points and it's on a function, I guess that's an easier way to
Yeah,
see.
that's exactly. If you remember what we did in the prerequisites lectures, the other lecturer, he said how if you have a curve, so if I draw this curve here, if you have a curve and if you draw like so if you have a curve like this, something like this, and if you draw vertical lines, they intersect the curve exactly at one point, right? So that's needed for a function to be well defined. This was covered in the prerequisites lectures. I believe I also put this in the lecture notes, if I remember. Yep, that's the definition. The relationship is that for each A, there exists only one B, so that you can map there. Okay. So that's that. Now you have to show that if you're so yeah, like Hoji said, the last part of the problem is basically just showing that a curve that is symmetric about the x-axis will not be like well defined because of how I explained regarding the vertical lines. So But the other part, you have to make argument in both directions. So you have to assume that, so first of all, you assume that x comma y lies on this curve, right? So your curve is symmetric about x-axis, and x comma y lies on the curve. Now from there, you have to show that x comma minus y also lies on the curve, right? So any ideas on how one can go about this? You have a symmetric curve about the x-axis. Your x comma y lies on the curve. How do you show that x comma minus y also lies in it?
Just solving for x gives you two outputs. Is that?
Can you explain like how solving for x would work?
I think it's working. Let me think. Wait.
Yeah, I think that's.
I mean, I think y has to be unique, right? If you want it to be a function. But if you think about what you can do, can you just how you mirror it? Like if you want to look at it, if you want to, I did not prove actually that it is symmetric. I just thought it was, we should just like find out, write that it cannot be a function because the y is not unique. But if you had to prove that, like on a symmetric graph, how could you just mirror the function and you work with that, or how would you do that?
Right.
Like how would you prove it?
Right. So when you have a symmetric curve over the x-axis, so if I draw the axis, bad diagram, but yeah. So this is your x and this is your y. So if I have some curve, I don't know, something like this. So this is our y equals to f of x. This is our curve. Now it's saying that this curve is symmetric over x-axis. So what this means is that this is exactly the same as this. So these two sides, these two parts of the curve are exactly the same. So that's why it's called symmetric over x-axis. Now, what you have to show is that for this to be symmetric, as I say, x comma y lies in the curve if and only if x comma minus y lies in the curve. So it's just like you take a point. Let me have another color. This is your point. You have x, you have y. So if your point x comma y lies on the curve, you have to check that when you drop this perpendicular and when it hits the curve again, you reach minus y. So this point that you reach, it should be minus y. This would be x comma minus y. And if this is exactly on the curve too, that's the first part of the argument, right? Now you have that in the other direction too. So you do the same argument. You say you take a function, you take a point, x. Let's say this time, x comma minus y. So this is on the curve. We assume that this is on the curve. Now you drop the perpendicular again. Perpendicular hits the other part of the curve. You check whether this is x comma y. So this is exactly what you need to do for the first part of the problem. Check in both directions. If it satisfies, you have the symmetric curve.
Oh, I thought we had to prove it like mathematical or something. Like plug in y and give it the same x.
No. This is like what I'm talking about in the like what it would look like in the geometric sense of the proof itself. Just means
Okay.
yeah.
Okay, sure.
Right. So that's what it means for this the symmetric about the x-axis. This is what it is. And now you have to explain why a curve that is symmetric about the x-axis is not a graph of a function unless the function is y equals to 0. So all he's saying that if you have this, this cannot be a function. So to show that this is not a function, all you do is you take one x, and you see that you're getting two y's for the same x, right? And that goes against the definition of the function. And you do that in the other direction too. So
I think I am getting it. Is it true that if we take one point x, then we will get two values of y, which is y and minus y? So this would mean that it is
sorry,
not a function.
couldn't hear you last part.
I think I am getting it. Is it true that when we take one value of x, then we will get two values of y, which is y and minus y? So this is against the definition of a function.
Right, exactly that. You just have to show that that is actually the case in a symmetric function.
And no value other than 0 can satisfy that both negative and negative. That can be both negative and the same positive. So 0 is the answer.
Right, yeah, he's saying that unless you have 0 for each value of x, you're going to always get two values of y, right? So I guess let's see. This is Michael's solution, beautifully LaTeX written. So he says a graph that is symmetric about the x-axis cannot be the graph of a function because it cannot be solved for a unique y. Yes. The rule for relations in set theory is that yes, you have citations too. That's amazing.
Damn, bro, nice.
Yeah, I was just looking online and I found like basic set theory, and that explained it quite well.
Right. Yeah. That's basically what it is. Okay. Wait, can you hear me, or am I being robotic?
I can hear.
I can hear you, but your screen is flashing a bit.
Flashing?
I think it's okay now.
Okay. Yes, that was problem 1.1. Yeah, 1. Then the second problem is the piecewise function. You have to graph this function, which has these two conditions. So when x is less than or equal to 1, you have 4 minus x to the 2x. And when it's positive, greater than 1, you have x squared plus 2x. Like anything that anyone just could not understand, like out of the problem, like I hope most people here know how to graph a piecewise function. We did that in the prerequisites lecture, but I guess that's clear with everyone.
Yeah, my question was that so like for the second part, x squared plus 2x, that's like fairly easy because that's a parabola facing up. But for the first function, 4 minus x to the 2x, like, I don't know like what the general shape of that looks like. Obviously I can plug it, some values in and plot it, but I was like wondering like if there's like a smarter way like to do this. I was trying to like find like where it would equal to 0, for example. I also found like what the function equals to at 1 on both sides. So this is actually, I found that it's a continuous function, and it's f of 1 equals 3. So the points connect at that point. But like this is x to 2x called, is it power function, or is it like some like I guess I have questions about like kind of general strategy for this x to the 2x portion.
Yeah, so this x to the 2x was kind of covered in what we were doing with the exponential functions. It's not directly related, but it's kind of like that. But let's see. Let's see if we can do this. Do you know what the graph x to the x to the like x squared? Of course, you know how it would look like. But you do know how x to the x would look like, right? F of x equals to x to the x.
If we put 0 in place of in the first function, would it get it undefined?
If you place 0, you'll just have 4.
Would it be undefined? Would it be undefined at that point?
I think 0 to the 0 is 1.
Yep. Anything to the 0 is 1.
Then there would be no problem.
Sorry, was 0 to the 0 1 or 0? It's 1, right?
1.
Yeah.
Yeah.
Okay, yeah, sure. Okay.
Yeah, and then so I think between 0 to 1, so it will be some fraction to the fraction power, which is going to be like a fraction to the square root. Not the square root, but some fractional root. But still, that will be so nothing is going below 0. And I think it will kind of come back to 1 again at 1, 1. So between 0 to 1, I think it will like dip down a little bit, like sort of like a parabola, but maybe not exactly. And then after x greater than or equal to 1, it will just be like an exponential, just like fly up.
Right. Yeah, this function is pretty interesting. So, let's see if we can like graph it right now and see what it would look like. And graph it in the sense like we did in the prerequisite lectures. So we see what the function behaves when we put different values to it, and see if we can like get an intuition about how the graph.
When I searched about 0 raised to 0, I got contradictory answers. So is it defined or undefined?
Can you repeat the question? Sorry.
When I searched about 0 raised to 0 on the web, it said that the answers were contradictory. Some sites were saying that it was defined, and some were saying it was undefined.
It is it's like the general agreement. Like the thing is, in mathematics, you have in some cases things are not like rigorously defined, but everyone agrees that if we accept this, things work nicely or things work as like logically. So with the case of 0 to the power of 0 is something like that too, where the possibility is that in some cases you can have it undefined, but in most elementary cases you can just take it as 1. So here we will take it as
1. Can I interrupt?
Yep.
Hello, how's everyone doing?
Good.
Good.
Yeah, good.
Good. I was wondering, does anyone have TensorFlow code to the processing of this the PSATs?
Code?
TensorFlow code?
We don't.
TensorFlow to process the PSATs?
We didn't use TensorFlow.
Okay. What libraries?
This is not really
You
about.
might be in the wrong.
Yeah, this is
Yeah.
this is just like a p-set of calculus, not even calculus, it's pre-calculus that we're discussing. Yeah.
Okay, all good. I'll let the class. Thank you.
Okay. Yeah.
Yep. Bye-bye.
So let's see what we can do with this function. So we have y equals 4 minus x to the 2x. So I propose that we first look at y equals x to the x. Can someone tell me what this would look like?
So point at 0, 1, and 1, 1. So wherever you want to draw that. I wish I could like annotate your screen. That would be nice. And then like between 0 to 1, it's gonna dip down, and then but greater than
Something like this.
Yep, and then back, and then greater than 1, it will explode.
Right.
And I guess undefined for x negative, because it will be imaginary, right? Yeah.
Right. Yeah. I mean, if you have x to the minus 1, you'll have minus 1 to the power of minus 1. There will be 1 over minus 1. But we don't really need to worry about that. But basically, this is your y equals x to the x. You can see how it would like behave. For example, if you put in different values, if you have 2, you'll have 2 squared, that's 4. So after you put in like a few more numbers, it's going to explode. So this point, this line, if I draw it a better color, this line where it starts kind of exponentially growing is actually 2. So 2 squared is 4. After that, any number you put is going to act like an exponential function. Right? Between 1 and 2, whatever you put in is going to have some kind of behavior like this. So it's not yet exponential, but it's going to be exponential once it hits 2. So this is how x to the x behaves.
Divya, can you confirm? So it's a tangent question. So among the kind of things that grow really big, e to the x, I want to just clarify the order, is e to the x and a to the x and x to the x. X to the x grows the fastest. I think that makes sense. Like 100 to 100 is larger than e to the 100.
Right.
And between e to the x and a to the x, which one grows faster?
You're talking about a to the x?
Yeah, where a is some like real number. Yeah.
I would assume that if you have a large enough, it's going to be
I guess a has to be greater than e. Yeah,
right, but it's still going to be less than x to the x.
Yes, yeah. I guess I was thinking x to the a, not a to the x.
X to the a would be if you have a sufficiently large enough, and if it's like larger than x, then of course it's going to be greater than x to the x.
Yes. Okay.
I mean, if you think about it, if you have x to the a, and a is significantly larger than x, and then x to the x is not really as large as wait, what was that? X to the a, because you have the exponent very large than the base and the exponent. So yeah.
Got it. Okay.
Mm-hmm.
And x, yeah, and then yeah, okay. And x to the a, I guess, is just like a increasing polynomial.
Right. You
Yeah.
don't. You
Okay.
like it's the exponent is not like a variable; it's a constant.
Right. Okay.
Yes.
Thanks.
So that is your x to the x. Now, how does 4 minus x to the x going to look like? I mean, that should be obvious.
Yeah. So it'll, like, flip downwards, and then I guess it'll be narrower because it's 4 minus x to 2x. So like you gotta kind of what is it? Squeeze it a little bit, I think.
No, we're not
Right,
yet at
yeah.
x to the 2x, just 4 minus x to the x.
Okay. So it'll be concave down, and also the point
It's going to start from would be
0, 4.
0, 4.
No,
Are you
0,
sure?
0, 3.
0, 3,
Yeah,
right?
sorry.
Yes. Does anyone have questions about like how it's going to start from 0, 3?
I think we're good.
Yes.
Sorry, if we. What was the question?
Yeah, the question was 4 minus. So now we're plotting 4 minus x to the x, and we're looking for how it will look like. And as I asked Jose, he said it's going to start from
2x.
3 and concave down. Do you know why that's the case?
X raised to 2x.
Sorry?
While you were writing, say, second time 4 minus x, there was 2 over there.
No, we have not yet got to 2x. We're just plotting x to the x.
Oh, okay. Yeah, 1 to the 1 is 1, so 4 minus 1 is 3. Yeah.
Right? Yes.
Yes.
So it'll go something like this, but it'll be concave down, and it'll be something like this. So this is your 4 minus x to the x. Now, if you've reached until now, x to the 2x is basically the same, but you squeeze this part a bit. If you squeeze this part a bit, you're going to get 2x. And how 2x would behave is that there's going to be, it would take a bit long. So it'll start from 3. Let me have another color. It'll start from 3, but it'll take too long to reach the line intersecting 2. Right? Yeah, this one, like, this is not it. It'll like take too long to reach this 2 thing. This line of 2. And that's like after which it blows up to being the exponential. So, yeah. So that is your 4 minus x to the 2x. That's the first half of the function. Then you have to put the second half, x squared plus 2x. So that's the easy one. But here I believe this is the graph of Michael.
Yeah. Oh yeah. Okay. What's the dotted point, Michael?
I just came out like this. I don't know. I just used an online tool and it automatically created it.
Right.
So I don't know why
Mhm.
I did it like this.
Yeah. I also like Desmos, the calculator, but I guess I was wondering what I guess the negative has to do with some kind of imaginary, but
No, I think
I
it's
don't.
just maybe because it's like in asymptote, it goes through to 4, but it never reaches 4. So maybe with asymptotes it does it like that. I don't know. I just used an online plotter that I found, and it just chose to do it like this. So I don't know.
I think the dotted lines, I'm not sure, but for some places the dotted lines would not be clear. That's probably the case. For example, oh, so you've like plotted this on this particular interval from -3 to, okay.
Yes.
That makes some sense.
I mean, I don't really know why it did like that. I know that there are functions that look like that have some kind of, that they are not, how do you call it in English? I don't know. They are not like
Linear?
durchgehend. Yeah, like they have holes, but I don't know what exactly is the reason for that in this case.
Functions that,
Sorry?
oh, excuse me. All good.
Okay.
Divya, what will be? We can cover this like later when we get to the like actual relevant point. But for the piecewise function, so it's continuous but not differentiable everywhere because at x equals 1, there's a sharp like turning point, like based on the graph that Michael like showed. Like so, like I can calculate the derivative of x squared plus 2x at 1, but like what is the derivative of x to the 2x?
Derivative of x to the 2x?
Yeah.
You'll have
So I
to.
know the derivative of e to the x is e to the x, and
Right.
derivative of a to the x is natural log of a times a to the x.
Right.
But I don't know, like, what would it be for x to the x in general? Yeah.
We'll get there, but you'll have to
Okay.
use like a function to the power of some function. So you'll have to use some kind of a chain rule or some kind of
Okay.
so if you have f of x to the power of g of x, right? So this is f of x multiplied g of x times. So you apply the chain rule a couple of times and you'll reach there. So there's basically a trick for it, but yeah.
Okay. 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 I think that makes sense.
Okay, so that was problem 2.
I reached the same conclusion, Michael, for number 3. It's like I don't think this is how we're supposed to do it, though. Yeah, I had the same. Yeah, like I got basically sine theta equals sine theta. I was like, this doesn't lead me to sine a plus b.
Yeah. I thought like, yeah, okay, I know now that it is correct, but that doesn't do what I wanted to do. So, but I didn't find out how to do it.
Okay.
Same. Yeah.
I'm not sure, but Calvin, have you tried this one? I haven't checked it. The trigonometry ones?
Yeah, the first page, I think.
That-
Is it there?
the-
Oh. Yeah, I kinda was like, what am I supposed to do? But
Okay.
yeah. But,
Yeah.
stuff
So
like
cosine pi over 2 is 0, so that term cancels. Sine pi over 2 is 1. So like that expression you wrote here simplifies to sine theta.
Okay,
But
sure.
I mean, and then we're all stuck there.
Okay, good, perfect.
Yeah.
On the same plane.
Okay, then. I think Siddharth has solved it, I guess. Siddharth, would you like to explain it yourself, or would you like me to explain? I mean, this is your solution, you can explain.
Although it was already, first we already knew the identity of cos A minus B, which is cos A cos B plus sin A sin B.
Right.
And then we were given the identity of sin. Sorry, I have written it wrong here. Sin theta is equal to cos pi by 2 minus theta.
Right.
Sorry, it's my mistake. Yes. So we were given the identity here. So what I did was I took general sine a plus b, just a general from any value sine a plus b. Then I transfer it to another cos pi by 2. Then I applied the identity on it and transform it to cos pi by 2 minus a plus b.
Right.
Then cos of pi by 2, then I just grouped them into pi by 2 minus a and just kept the minus b.
Yeah.
So we have it out of the form just like in the about cos a minus b form.
Right.
Then applied the cos a minus b identity. So this was where I got. Then as we know, cos of pi by 2 minus a is just sine a, and sine of pi by 2 minus a is cos a. So sine a cos b plus cos a sine b is the expression for sine a plus b.
Right.
Oh, okay.
That's exactly what you were supposed
Thank
to
you.
do. Yep.
Okay, I'm good on this one. I
Mhm.
guess we all just try to just substitute in like a equals pi over 2 and b equals theta and just but yeah, this makes sense to me.
Mhm. Yeah. Also, by the way, would you guys like to like make the solutions like accessible? Like, would you guys like want to see each of the solutions? I think I can make a GitHub repository or something where you can download each of the solutions. Do you think that'll
Sure,
be
that's
good?
possible.
Yeah, I would not mind it. I didn't submit one for this time, but in the future, if I submit one, I don't mind if it's posted on GitHub. I think it's nice to see how other people are thinking, like when you read
Right.
their solution.
Right.
Yeah.
And also, it helps us like keep a record of like when we did this, like we had these solutions, so we can go back when we do it again. So, yep. So that was problem 3. Also, hello Bobby Wang. We're discussing some problems on pre-calculus. That was problem 3. Problem 4 is you have to graph this function cos of x minus pi over 2. I guess that's kind of the most straightforward question in this problem set. But like, what do you guys think?
Yeah, so the period is just the same because it's not sped up or anything. It's just shifted
Right.
to the right. So I hope I'm right. Right?
You are, yeah. To be honest, like why I put this question is that to kind of like make you guys inquire about why like this cosine and sine functions give a wave-like graph. I'm not sure if you guys already know why it is so, but that's part of why I put the question.
I mean, it's a circle, right? If you have a circle and you carve it up and you could take this and just build a circle out of it, and that's why it's p and goes to p and 2 times p. Right?
Right. Yeah, that's the exact intuition behind it. You have the circle, you keep rotating it, you'll get back to the same angle, same values again, and that's your period.
Yeah.
Okay, so that's good. Everyone's clear on that. The graph is going to look exactly like this, and yeah.
We can just say it's exactly the same as the sine wave.
Right. Yeah, he did it here. So he wrote cos x minus pi over 2, took the minus out, and he'll get sine x. So this is the same old sine function. Yeah. And yeah, cos is an even function. I believe we didn't introduce this when we were doing the prerequisites lecture, but does anyone know what an even function is in contrast to what an odd function?
Yeah, even function. So if f of x equals y, then f of negative x equals y. An odd
Right.
function, if f of x equals y, then f of negative x equals negative y. And
Right.
it's also like a reflection across. And then is it a reflection across x equals y? Y equals x. Sorry.
Not sure, but I think.
think
Go on, Michael.
yeah, just maybe but I thought I like read about it like OJ said with the x, you do like a line at x is y, and then you just mirror it, right?
Right.
Yeah. Yeah, and then even function obviously is a reflection across the y-axis.
Yes. So your even functions are symmetric about the y-axis, and that's the other way around for odd functions. And all you need to remember actually is that if you have an even function, f of x is equal to f of minus x, as Jose said, and for an odd function, f of minus x is equal to minus of f of x. Yeah, so that's another approach. You can just like simplify this trigonometric function, get something more simplistic, and then graph it. That's one of the ways when you try to graph complicated trigonometric functions. Okay, now we have transcendental functions. The first one is the natural log. How many people don't?
Actually, I'm good with 5 and 6. So I think I mentioned this as a problem, but actually no, I can do 5 and 6. So
Okay, that's nice.
By the way, what do we mean by transcendental functions?
Okay, transcendental functions. That's a good question. So let me see how I can explain without analysis, but yeah. The transcendental functions are, as you can guess, they're a special kind of functions, but they are functions that don't necessarily have a polynomial equation. In an algebraic function, in a normal function like, I don't know, x squared plus 3x minus 4, that's an algebraic expression, that's a polynomial, you have a parabola, graph, whatever, you do that. But in the case of transcendental functions, you don't have a polynomial, like an elementary or algebraic polynomial. You don't have that for this function. So that's, I believe, the way you can understand it. There are other cases, other properties, but this is the basic definition.
Got it.
So like logarithm is one of them. You have hyperbolic functions. There are other like very specific functions like the zeta function, gamma function. There are functions that do specific kind of things, and they're called transcendental.
Does all E-type functions come Euler number? Any type of Euler number function comes under this transcendental?
This E is actually not the Euler number. That's so E is the Napier's constant. That's bad because like this E is actually used as a notation for a lot of things in mathematics, and that's confusing. But E actually doesn't come from Euler's any kind of constant. It is actually from the definition of logarithms. So Napier was the guy who came up with logarithms, and he then came up with this constant. So this is actually E just comes from logarithms, at least here.
Are they both same or different?
Which one are you talking about?
Euler's and Napier number.
Euler's number. is again. But the thing is, Euler's number is the same thing. Of course, it's the same thing. Like the number, if you like look at the number itself, is the same thing. But the way to think about it is different, because Euler's number, the constant itself, doesn't mean anything about the function. The exponential function is separate from the number. So that's one of the ways. I think we're going to see this later when we go to the end of this course. We're going to see something called Taylor series, and you will see how you can write the Euler number as a way of like infinite series in an interesting way. So that's probably would make it clear why Euler number is equal to this function.
Yes.
I think I got to the point in the middle of the course where E was defined as a limit as 1 plus 1 over n, all of that to the n, like that.
Right.
Yeah. So is that not how? I guess I'll maybe just figure out later, like how that's also related to Taylor series. I can.
Yeah. So you have 1 plus 1 over n to the n, and if you take the limit of this as n approaches infinity, so this happens to be equal to, and if you play around with this limit, you'll be able to find the Taylor series for Taylor expansion, whatever they call it, for E. So how the Taylor expansion looks, maybe that will give a bit of an idea, intuition. The Taylor expansion is basically summation from n equals to 0 till infinity of 1 over n factorial. Okay? So that looks like 1 plus 1 over 2 factorial plus 1 over 3 factorial. Continues. Okay? This is exactly right, and we'll see how this is related to the derivative of e to the x, and why e to the x, when you integrate, sorry, when you take the differential, the derivative, you're going to always get the same thing back. It also is related to the Taylor function, but yeah, this is one of the interesting things.
Why is every Taylor series defined in terms of factorial? I don't have any idea since I have not read rich, but why is there factorial in every Taylor series?
So factorial is just like, again, factorial is not like it's just a way, it's just shorthand for writing things. You can, like, when we did not have factorial, which is like multiply, we wrote like 1 times 2 times 3 till n. So
from 1 to, if there is dependent factorial, then we shall multiply all the numbers from 1 to n.
Right. So the reason why in Taylor series you see things getting multiplied all the time is basically because you're trying to sum things up. Sorry.
Yeah. I think this is like coming from, like, if you take multiple derivatives and apply the like not the product rule, what am I saying? Like if you take the continuous, like a derivative of x to the n, and the first derivative is like n times x to the n minus 1, and the second one is n times n minus 1 times x to the n minus 2, and then like if you keep pulling it down, you like multiply n times n minus 1 times n minus 2 times ... And I think that's like sort of where the exponent is, the factorial is coming from, I think.
Yeah,
it's somewhere related to that, I think. Yeah,
right.
so somewhere in there.
That's exactly right. But that's just for this e to the x. What about the Taylor series for sine? sine of x. You don't really have.
Okay.
But you always
see.
see the factorial there too. But yeah, in this case, you can say perfectly that this is because of the derivative of x to the n and xn minus 1, and it keeps repeating. So yeah.
When finally the n minus 1 and n minus 1, when you differentiate till you get to 1, then you will get a factorial, right? N factorial.
Yeah. The goal is when you keep on differentiating and you keep on multiplying repeatedly, you'll just get n times n minus 1 times n minus 2 up until you get to 1. That is just n factorial.
Yes.
Yeah, there's a bit more on that because you have different types of infinite series. You have Maclaurin series, you have Taylor series, and stuff like that. Probably this course is going to tell you a bit about those things, but you'll see how even if you don't have always these exponents, you always see these factorials. So. Anyways, going back to the P set, 5 and 6, is anyone confused, or is everyone clear on solutions?
Yeah, no, I was confused, but maybe I just should learn the rules better of how do you say that?
Logarithm?
Turning them into components and then solving it.
Okay. So this is your solution, right?
Oh yeah, maybe not show it. No, it
It's fine.
really sucks. Is this a bit what you should? I mean, is the first step correct?
So you
Or-
did.
That is the right rule, but I
Mhm.
don't. I think the first step is to apply both sides the exponential function.
Instead
Yeah.
of doing this, we can convert into e raised to, since next.
Right. That's what you said. Yeah.
Okay, so this wasn't the useful step. So just keep it in. So e to the power of
I think.
2.
Yeah. So this is a Siddharth solution.
I mean, what I did was first that I like put the one part on the one side and the other on the other. Then you have like this e square is equals I don't know, and then you can do the ln.
Yep.
And if you do that, then it's a lot of like shoving stuff around. Yeah, you're trying to get from there to there, and after you do a bit of I don't know how you call that in
Manipulation, yeah.
English, but you do that in German. It's Umformung. So yeah, like you like juggle it around, and
Right.
after some time you get to the point where you have t on one side, and then I also tried to like put in the numbers, but the problem is that the number is not correct. The number it's not 100%, so I left it as in this term, because if you
Right.
like put in the number, then it's not really useful.
Yeah, it isn't. Yeah, I mean, the problem probably just ends if you have value of t in terms of e. So.
Yeah.
Okay, yeah, makes sense. Thanks. And the second one.
Yeah, the second one is this one, e2t is equal to 3et. I believe this one is much easier than the last one. Yeah.
Yes.
Basically, you just take 3et to the other side, you do some algebra, you get et equals to 3, and yeah, basically that. This is Michael's solution. So.
I mean, I found no solution, so.
I think the step that you got wrong is like on the second step from e to 2t. When you take the log on the right side, it is I think it's going to be t times log 3. Is that right?
And I think I'm getting a solution.
Oh, Siddharth, you're getting a solution?
I don't
Yeah, maybe.
stronger, right?
This is Siddharth's solution.
And I got ln3 equal to t.
I think you're right. Yeah. There's no solution. Yeah.
Okay.
Natural log of 3.
Right. So,
Okay.
yeah. So he has. This is actually the way you should be doing it. You will have two cases when either e to the t is 0 or e to the t minus 3 is 0. And
Okay.
so when e to the et, so this is the part that Michael did. When e to the t is 0, you have no solutions. But when e to the t is 3, you have, of course, the solution. So, yeah.
Oh, that's interesting. Yeah, I should have done it like that.
Oh, you explain how to calculate log 3 again? That's nice. Okay, so he got a fair approximation of what t would be like by root computation. That's nice. That's the value. Okay, so that was.
What did I do?
Sorry?
What I clearly did it wrong. 1.3, yeah. Where did I go wrong? I tried to factorize the e instead of e to the power, and then it just completely messed up somehow.
Let's see. So, wait. You had e to the 2t is equal to 3et, but e to the 2t is not equal to e to the 2 times e to the t. That is 2 plus t, not 2t, right?
Ah, shit. No. Okay.
That's the
I gotta
basic.
learn his
Yeah.
basics.
Yeah. So that was 3 and 6. Sorry, 5 and 6. The binomial theorem part. That's probably the most interesting part of the PSAT. Problem 7 asks you to give both an algebraic and a combinatorial proof of this identity that we have here. The algebraic proof is basically just computing the two sides and you'll get the same thing. The combinatorial proof is more interesting. So, how do you guys approach this?
First, I just tried to expand it,
Right?
but then it came, quite hard to progress.
Okay. So the thing is, you can prove things in all kinds of ways. But normally when you're proving identity, all you need to do is just compute the left side, the right side, and arrive at the same thing. That's the proof. But other ways there are, like I think Michael mentions it, the induction. But I don't expect people to use induction because we did not get into proofs. But you can use induction on n+1 and you'll arrive at the identity in the exact manner. But all I wanted is basically compute both the sides and check that they're the same. That's the algebraic.
I guess. Yeah, I guess maybe I'm the only one who's not getting even the algebraic one. Like where I try to expand it out using factorials. I don't know how things cancel with each other to get the same expression as the right hand side.
Okay. Let's see.
Yeah. I can possibly try to share my screen. If
So you've made some
sure.
progress that we're trying to show.
Yeah, I can write like quickly.
Okay.
I'll try. Let me see. Oh, I need to give some access. Sorry, give me a moment. If it doesn't work, then that's fine.
Yeah, I mean, do you know LaTeX or anything like that?
Okay, so I do, but I'm not really good at like typing very fast.
I mean, you can take your time and write it
Yeah.
in the chalkboard, because we have the LaTeX bot, so that might be a bit.
Okay. Okay. Okay.
Yeah. Otherwise, I'll just compute it now, and we'll see.
Okay, that'll be better. Yeah, because also if I try to share a screen, I need to reopen, like quit and reopen. So I don't want to do that. So okay.
So yeah. So basically, you have to compute the two sides. Let's see the right side. The right side is basically n factorial over n minus k factorial times k factorial times k factorial over k minus 2 factorial times 2 factorial. I'll write this down. I'm just computing it. I'm thinking it aloud. You cancel k factorial out, and you'll have n factorial over n minus k factorial times k minus 2 factorial over 2 factorial. You'll have to do a bit of manipulation there with regards to k minus 2. The k minus 2 factorial.
Yeah, so far I'm following you.
Sorry, but I have to go now.
Oh,
so thank you for the lesson, and see you. Like probably not. I don't know if I can come next time because I can't really come 3 times a week. But I'll try to like.
Yeah, join whenever you can. Yeah.
Yeah, sure. Yeah. So thank you again, and have a nice day.
Yeah. Good luck for your exams.
See ya.
Bye-bye.
Bye.
Okay. Yeah. So let me actually compute this whole thing. Yeah, the algebraic proof. That's why I put both the proofs, because mostly the algebraic proof is not that interesting, so just computation. But the combinatorial proof is more interesting. Let's see. We'll do both of them. Yeah, give me a minute. I'll be right back. Okay, I'm back. So I'll try and write this as I compute in the chalkboard. Hopefully I don't make any typos, because these kind of problems are not the best problems to do, but let's see. You have n minus 2 factorial over you'll have n minus 2 minus n plus, so you'll have k minus 2 factorial. Times k factorial. Right. So, okay, I'm doing it from LHS. Let me write that. So, this is this. When you expand it further, that's well.
Oh, sorry. Maybe for the sake of time, maybe we could talk about the combinatorial, which you say is more interesting. Like I think for the algebraic, I can at least sit down like after this
and compute it. Okay.
For it. I know you have written a little bit already.
Right.
Yeah,
right.
but I also want to make sure, I don't waste time for other people.
Yeah.
Sorry.
No, that's okay. I think like, what about others? Have others like completed the algebraic proof?
I have not completed,
Okay.
but I'm trying now.
Okay. Yeah. Do you?
No, I couldn't.
Okay. Do that, and we can talk about the combinatorial proof. And if not, I'll like do the computation. I'll write the LaTeX later, and it's just a matter of checking things out. There's nothing really liable in it.
Right. Yeah. I guess I just need to, actually practice, brush up.
Right. And if you're interested in like the book that I got this from, I mean, this is a typical problem, but this is basically from this book. Not really this book.
Oh, elementary number theory? Oh, interesting.
Yeah, this book is like a good book that I used a long time ago. But the first chapter deals with the prerequisites and the binomial theorem. It had a good explanation, so from that. But the goal here is just to get used to how computation works and how we can cleverly cancel things out.
Right.
So this is basically.
Didn't you send me a different book, or is it just another? Thought you sent something else, right?
Yeah, so the one that I sent you was like, I had the combinatorial proof and stuff like that. This one doesn't have the combinatorial proof. This is just like basic algebra.
Okay, yeah.
But so this problem that I've given you, you can see that this looks a lot like this. So this is a Newton's identity. So Newton, when he was coming up with the binomial theorem, this is one of the identities that helped him come up with that.
I see.
Right.
Oh, cool. Okay. So this is the. So basically, the question was asking for like check that the Newton's identity is correct, algebraically and combinatorially.
Right, basically, and in our case, we have r is equal to 2, as you can see.
Right. Yeah.
I could have done that for like r equals to, what is it? Sorry, r equals to r as a general, but I believe the combinatorial proof is not going to work in general, so I put some number there.
Gotcha.
Okay. So let's look at what it will look like in the combinatorial proof. So if I open the book that I was looking at, so this is another good book. Probably not for. It depends on what your level is, but this is for Olympiad problem solving, and it assumes that you've already done calculus before, even though most of the book doesn't deal with calculus stuff. But
this book by Paul Zeitz, right?
Yep.
Yeah. I have met him actually. Like I used to work at like Berkeley Math Circle, and he was like a frequent lecturer there.
Right.
Yeah.
You've been to Berkeley Math Circle?
And not as a student. Like I was an undergrad there in Berkeley. And so technically I should know all this stuff, right? But I guess like my major went off. It was not in math, and
okay. It's been a long
to
time.
kind of like relearn kind of this. Yeah, it's been a very, very long time. So yeah, and I thought I might just start from like multivariable, but then I was like I want to start just from scratch, like go from calculus and
right.
So yeah.
That's a very good idea. The thing is, it's good to know that most people here are kind of like that too. For example, the Michael we talked to this time, he's as he said, he's completing his bachelor's in computer science, but he has done all of this a long time ago. He's probably in 30s or something. I'm not sure if I remember, and he's coming back to this again. So I'm glad that
in Berkeley Math Circle, I was just like an admin, like so I was admiring all these like really small kids doing math that I don't understand.
Makes
and
sense.
I guess maybe I will not reach that level, but I guess I kind of want to learn. So yeah.
Yeah, Berkeley Math Circle, I've heard a lot about it. It's an amazing place. If you know a bit more about Paul Zeitz, he actually started a school called the Proof School.
Yeah.
Right? And he's like teaching kids up until like high school. And
yeah,
that's amazing actually. Yeah. So what we're visiting from this book is this part on Pascal's triangle and binomial theorem. So in the prerequisite lecture, I kind of gave people an idea about how you can make arguments about the binomial expansion by pure English words, just counting things, right? And that's, to be honest, if you ask me, that's one of the great skills to have, to turn mathematical expressions into just language and explained in words. And that's fun, but also something you would have to practice. So in this book, you're going to see a lot of the proofs done like that. You'll have just by rules. So for example, this is the combinatorial proof of the binomial theorem. So here, if you have seen a proof of the binomial theorem, it's just like expanding things, a lot of algebra, cancellation and whatnot. But here, he kind of like asks you to think what this would look like when it expands and when you count it. So what happens is that he of course gets to the answer, which is 7 factorial over 3 factorial times 4 factorial. That's the answer to x plus y to the 7th. But he reaches that by just counting things. Okay. So I'll prove.
Oh wow!
Right?
Wow, this is really clever. Yeah.
Right? I'll post this thing in the chalkboard, and I'll let you guys take a bit more look at it and try to understand.
I get the general like kind of approach, but that I would have probably never thought about it.
Right. This is very clever, and there are actually very interesting tactics. So I did Olympiad math a long time ago, and combinatorics was the worst. Mine, I had problems like counting things a lot of the time, and I didn't like it. But in the process, I did learn this skill which is very helpful. If you go a bit
Okay.
before, so he defines what a combinatorial argument is. So you see these, for these expressions, he has like simultaneously the algebra and the combinatorial
Oh,
argument.
and like, cool. Kevin, is this the book that you got from Divya? I remember I
Yeah,
just posted a
yeah,
question on
yeah.
Checkpoint.
Yeah, this is the one, and then yeah, it looks really good. So I really want to read this. Haven't read it yet.
Okay.
Yeah.
Okay, so I'll probably like see if I can find some free PDF of like this one and also the elemental number theory.
I'll post the free PDF of this one because it's like under 8 megabytes, but the other one is like 30 or something megabytes. So I'll probably post like a drive link or something like that. But this one is you can have it. So like.
Oh, thank you. All right.
Mm-hmm.
No, I just saw in your shared screen that
Mm-hmm.
she said something to me. She, Hojie.
She.
She. Let me see. Yeah, this is what you meant, right? Just this. You're
Yeah.
interested in this book, yeah. Okay. Yeah.
Okay, so I would encourage everyone to go through this and try to figure out how to think about this. I mean, it doesn't matter if you prove this or not. It just matters if you can learn how to think in this way. So this is a good example. So here you have 17C8 and 10C2 multiplied to each other. Now, how do you make sense of this inverse? He says the number of different teams of 8 girls and 2 boys chosen from a pool of 17 girls and 10 boys. So there are a few things to put emphasis here. First of all is that he's using and instead of or. When you're using and, you always have multiplication happening, right? So here you have 17C8 and 10C2 being multiplied, so you're going to choose and. If you're not familiar, the best way to think about it is that like you can do something, like you can do a job A in 7 ways and you can do job B in 8 ways. So in how many ways can you do the job A and B? It'll be 7 times 8 in 56 different ways you can do job A and B, right? So that's the idea here. Now,
yeah, I think I get the and. The or is a little bit non-intuitive for me, that you do the sum, the one below, the number of ways picking a team of 3 or 4 people chosen from a room of 17. I guess that makes sense. Never mind. Yeah, like you find a way to choose 4 people, and then you sum with the number of ways you can choose 3 people.
Right.
Yeah.
Why use or for summation is that you have 3 ways to do job A, 4 ways to do job B. So either you do job A or B. Like if you have or, you're like, you know, kind of like I mean, you can think about this. If you have A or B, it'll significantly be lesser than A and B. That's the basic intuition. It'll be significantly less.
Okay.
But then, sorry.
Well, I think that when we have or, we usually make cases. So there are 2 cases here. So we add.
Yeah.
While in the and there was only 1 case.
Yeah, that's.
And they were both a part of 1 case, so they are multiplied.
Right. That's a very good argument there. You have in or you have like you find some ways by case 1 and you find other ways by case 2. Now to get the total number of ways you add what you get from case 1 on case 2. So this is why you add. That's that. And about permutation and combination, how do you make arguments for that? For example, 10C4. This is the number of ways of choosing a team of 4 people out of a room of 10 people, right? And where, like, it doesn't matter how, in what order you pick the people, right? So this is how you should think about 10C4 or KC or whatever you have. And P10-4, that's the permutation. So for that, you'll think the number of ways of choosing a team of 4 people out of a room of 10 people where you have the order that does matter, right? So it's kind of like we first, as he says, we first designate a captain, then a vice captain, co-captain, then manager and whatnot. So you have to like reduce the number of ways to this kind of ordering. So
Right.
that's the basic thing. Now for like yeah, he makes you do this the symmetry identity. So the symmetry identity is basically this: NCR is equal to N minus R. You can check this algebraically. It's easy to check. But trying to
I
make
think I kind of found out like that it's true through get you know, but I think this one I figured it out like even though I'd never like seen it in like a definition form.
right.
Yeah. Okay. I think for were you planning on going over the optional questions or
if people want to, I can do that. But as the optional things are not part of the course, we're not going to use complex numbers ever in this course, so it depends.
Okay.
Are we doing the ninth
Sure,
one?
but it's fun. So
Sorry?
Are we doing the ninth one?
The 9 and 10, if people want, I can like give a quick explanation, but
yeah, sure, it's fun.
Yeah.
Even though it's not necessary, it's a quick view on how to do it. It's
right.
probably useful someday. So
Okay, yeah. Give me just a minute. Okay, so complex numbers, do you guys like have an idea about complex numbers? Like, how do you think about them? Any previous experience?
Yes. I'm in 11, so just encounter.
Okay, yeah, you just encountered it. Makes sense.
I didn't quite hear it, but a complex number is like every number, right? Because a complex number is a real number and an imaginary number, and you can set each of those to 0, so it encompasses all numbers. Is that true?
Not exactly. For
I can
example,
just say
you can't write 3 as a complex number, can you?
Really? Okay.
can you please repeat?
Yeah, you can't write 3 as a complex number. 3 is a real number.
But we can write it as 3 plus 0i.
I mean, like for 0i, you basically get the real numbers.
Yeah, that's what I meant. That therefore complex numbers are all numbers, real and imaginary, because complex is a combination of the two.
No, I mean, like if you think about this, like whole numbers are like a part of natural numbers. Does that mean natural numbers kind of? I mean, of course, you can think of it as a subset of the real numbers. It's not even a subset essentially. It's kind of like you use real numbers to like have another kind of numbers called complex numbers. It's not that one encompasses the other entirely or something like that. So what this means is that this book again has a very nice section on complex numbers. So the complex numbers are often represented with this this kind of way. So what you have is this is the real line, and this is the vertical axis has points with I as they're like multiplied to them. So you have IB, IC, whatever on this axis. So the complex number you can see as the quote unquote norm of this. So if you know what a norm is, it's basically just taking the length of this line. So you have this component A and this component BI. So if you need a length for A plus BI, what you do is just take the square root of A squared plus B squared. So that is all what the real number is. You'll have to know that you have two axes. So you have the real axis and the imaginary axis. So that's two axes of the complex plane. And yeah, that's basically it. You know, z is equal to A plus BI, and the absolute value of the length of z is equal to root over A squared plus B squared. There are other ways to think about this. If you go into complex analysis, you'll know more for like why things are the way they are. Complex analysis is not a very hard subject to go into. For example, if you ever intend to, I have never gotten into complex analysis. This book is often recommended. Visual Complex Analysis by Needham. And it is geometric and very, very good at explanation. So
Thank you. Can I ask like a sort of a related question? Like in my like matrix algebra class, I remember like professor using like for matrices, there's instead of using field of reals like the R with a
right.
extra, or the field of complexes, complex numbers like C with the extra line. He said like like a lot of these theorems apply to just like a field of just he uses notation F with the extra line like with a special I guess just fields. So does real and complex make up fields, or like what is the F field that he was talking about? Or
okay.
or,
So
or that.
yeah, probably you're
I guess
like.
I was just wondering.
Did you remember what course was that?
There was that MIT course. It was just a course that I took in class. I
mean, yeah, like
it
what
was like
course he was teaching?
It was, I think, matrix theory for signal processing.
Okay.
But it's probably like advanced linear algebra, I guess,
Right.
or just linear algebra.
So, of course, it takes a few things to explain what a field is. Basically, in linear algebra, you have vector spaces.
Right.
So vector spaces are a special case of something that is a bit shy from a vector space. So you have modules. So modules are kind of vector spaces, but they lack a few conditions which doesn't make them as special as vector spaces, right? So how do you create modules? Well, you create modules from something called a ring. Well, ring, if you remember what a ring is, if you have seen it, ring can be the integers. The integers form a ring. It's basically a set with multiplication and addition and some other special conditions. So the field is something that extends from a ring, which acts as the basis for a module or a vector space. Most of the time, a vector space. So field is something that helps you define what are you going to do in a vector space. Where are you going to get these elements from? For example, if you have a matrix, so where do you get these entries from? Where do you pick this from? Sometimes you pick them from reals, sometimes you pick them from the complex, otherwise, right? So these entries that you pick from, the set that you're picking it from is called the field. So yeah, that's basically the idea.
And like the real space is basically the field is that we're going to pick from real numbers.
Sorry, I couldn't hear you, the last part.
So I guess the field is a way of picking from like a set of numbers.
They're not always numbers, but
Okay.
as you saw, they can be complex numbers. They can be just abstract elements in a
Okay.
set. But what it means is that field is not a way, but it's kind of like a set in itself, but it has some specific properties which lets you
Okay.
choose things from it so that you can do a few
Okay.
things. For example, the field R has its properties, right? It is commutative. It has real numbers in it.
Yeah.
A few other properties, but the complex plane is not like that. In complex plane, you have the conjugate, complex conjugate, and other properties. So field is basically set with a bunch
Okay.
of properties, and which help you
Okay.
define things on vector space. But yeah, this is
Okay.
linear algebra, basically.
Yeah. Okay. So yeah, okay, got it. So like an example of a field would be like R or C,
Yeah.
but not Z because Z is a ring and it doesn't. Yeah.
Yeah.
Is that right?
Yeah, Z
Okay.
cannot be a field because it lacks a few properties.
Got it.
Mhm.
Right, thank you. Yeah, that's a odd digression, but yeah.
Yeah. Okay, so this we go back to complex stuff again. But yeah, this is basically it. You check out a few of the properties. For example, I talked about the conjugation. So what a conjugate is, you have Z as a complex number. You write it as A plus BI. The conjugate is basically A minus BI. So when you you can think about it, right? For example, when you multiply
Yeah.
Z times Z bar, what are you going to get?
You're going to get I think A squared minus B squared.
And what is that?
I think A squared plus B squared.
A squared plus B squared.
Yeah, A squared plus B squared. Yeah.
I get squared and it
Awesome.
converts to A square plus B square.
Right. So that's basically if you remember what that is just the length of the Z squared, right?
Right.
So that is your conjugate. A few other things that are also necessary is that when you're talking about complex numbers, you should always have this diagram in mind with a vector which rotates around the origin with this angle. So why to think about that? Because it gives you this nice representation. So you can write complex number as its length, so R is its length, times cosine of the angle it makes with the x-axis, and I times the angle, sine of that angle. So this is another form of writing the same complex number, but with just its length and its angle. You don't use A or B. So that's another way to use it. You're going to use it later in multivariable calculus all the time, but here it will not be used.
I never seen a notation cis like with a capital C like that.
Oh,
I
this
think
one?
that's my first time. Yeah.
Oh, this one is basically just like an abbreviation of.
Right.
Yes.
Yeah. I guess I've just never seen it in my life, which is interesting.
So you see how the addition is going to work, and a few other things is going to work as it does in vectors, if you know vector addition and stuff like that. But yeah, algebraically you can think of it like if you have two complex numbers, you're going to add the real parts separately and the complex parts separately. So this will be A plus C plus B plus D I. The multiplication works as you would expect it to. But I believe what I would yeah, so this is another important thing in complex numbers, that you can write them as the exponential form. So
right.
You have the Euler's formula, if anyone has seen it before, that e to the I theta is equal to cosine theta plus I sine theta. That's a formula which helps you make sense of the complex number. So this is very helpful because when you have like complex plane, you can reduce things to this exponential function, and then differentiation is basically easy because you have the exponential
Right.
function. So this can be very helpful at times.
The above theorem is quite interesting as well. The Moivre theorem. It's 4.2.6.
Yeah, the de Moivre theorem.
It's just like there's no like expansion like the binomial theorem, but you can just kind of put the exponent n inside the
right
cosine and the sine. Interesting. Okay. Okay, this is for any integer n.
Yep.
Okay. Yeah, but I guess it's not true for like other values in the real, like rational.
Of n?
Like, yeah.
No, it is just for positive. No, it's
Okay. Oh, so
positive
it
and
is
negative. Yeah, it's the integer n.
Okay. So only interesting. Okay.
And this identity is actually something you use a lot of the time to simplify computation. And the proof of this is not that hard, but it can be a good exercise of binomial theorem if you try.
Yeah. Maybe I will try. Yeah.
Okay, so if we go back to our problem where what we had was basically okay, so I'll solve problem 9. The 10 is nothing other than just solving the quadratic and putting it in terms of complex numbers. This one is more doable, but 9th one you'll have to mess around a bit. So
By the way, could you check, is my answer right?
oh, you've done
I got
that?
y.
Okay, I didn't see.
Yes, I got y equal to minus 1 by 5 and x equal to 2 by 5.
Okay, so we'll follow this and we'll see how far it goes. So you have okay, yeah, I'm ready. So what you do is you first have I plus I or 1 minus I squared.
So I multiplied with the conjugate.
Yep, I see that. Multiply the conjugate on the numerator and denominator. So here, if you remember what the conjugate is, this one will be 1 minus I, this will be 1 plus I. Multiply that, you're going to get 1 plus 1 and 1 plus 1 times I up there. Right, yeah.
Then I just multiplied x plus y with the minus 1. Then multiplied with the other side. Then sent to the other side. So
right.
so then I got this. Then I took minus common for convenience.
Right.
I could directly compare.
Yeah. So this is, I'm not sure if Calvin is aware of this, but some of the times when you have equations on both the sides, and you have like x and y's, what you can do is you compare the coefficients. So here, the coefficients are more, figure them out what they are. You just compare the real part of the complex number and the imaginary part. The real part is 1 minus x and x minus y. And the imaginary parts are minus y and minus of x minus y. So you compare those things, you equate them, and you get equations. And from those equations, you can solve things. So that's exactly what Siddharth does. He equates y with minus x minus y. So you have y and minus x minus y. You equate that. You get 2y equals to x. 2y equals to minus x. And he equates the other half, 1 minus x, x minus y. 1 minus x minus y. So you get from here that 1 plus y equals to 2x. Now you use this to solve this equation, just like linear equation in two variables. You get a value for y, you put it there. So yeah, this is good.
I see. Oh, okay. This is how. So yeah, in first glance, I was wondering. Okay, there's one equation but two unknowns. But the way that you solve it is that you can actually get two equations by looking at the real and the complex sides,
Right.
kind of separately. Yeah. I think I got through like half of this problems, and okay, I'm good with this.
Cool. Calvin, do you understand too?
Yeah, well, yeah, vaguely.
Vaguely, or is it
Yeah.
vague?
No, just like it's completely new to me, complex numbers. So
Yeah, I mean,
so yeah, I think
you can
if I
probably
were to
just
calculate, oh, sorry.
right, just probably just completely forget that complex numbers are a thing. Like this proof, so this thing just needs that I is equal to square root of minus 1, and basically that. Like with that, you can just solve the equation, compute it. You don't need any knowledge for complex numbers either.
Okay, cool. May I ask what? Oh, may I ask what complex numbers solve exactly? Like what is the problem that was there before the invention of complex numbers? Why is it?
Basically this I is the root of all evil. It's equal to square root of minus 1, and you can't actually evaluate it. So they used I to define a whole coordinate system, number system, but that's the complex.
Yeah, but what does it solve to gain another axis?
It solves solves a lot of things actually, but what you get is essentially new kinds of functions that are much better than real functions. So one of the other reasons why people love complex analysis other than real analysis is that the functions, the complex functions, are actually infinitely differentiable all the time, right? So they're smooth.
That's cool. Wow.
Right, so you can take derivatives as many times you want, and you would not be stuck anywhere. But in real functions, you have cases where, like, the whole goal of real analysis is to show you how exactly you cannot differentiate all functions and all the conditions why you can't. So that's one of the real good things about complex analysis.
That's really cool.
Yeah, I've no big picture about why. Okay, thanks. I'll probably I'll probably understand it better when I go further into the math.
Yeah, I mean, it's one of the ways to kind of gain a new insight about the existing things. For example, the thing that I just showed, the polar coordinate system, that basically arose out of the complex system. So this was a good way of like using the real numbers and the angles to represent things. Probably you will understand more of its importance when you do multivariable calculus. That's where it kind of is important. Yeah.
Okay, thanks.
Sounds good.
That was 9 and 10. I would encourage to just
Was that
compute
answer
it.
correct?
You solved it against that? Okay, you substituted x squared for t. Right, that's basically, as I said, solve the quadratic. And you'll get one of them as complex numbers. Two of them as complex numbers, of course, because your discriminant is negative, right? I'm not sure if you know this before, but when you did do quadratic equations, quadratic polynomials, you had a way of finding the solutions. And remember this d, which was inside the radical, the square root. And d is kind of everything that drives the solution for a quadratic equation. And when your d is negative, you can't have real solutions. So that's why also we need complex numbers.
Right. Okay, I made some algebra mistake on this one, but okay, yeah. Wow, I really need to even basic algebra. I need to brush up. I think
Oh,
that's okay.
you mean like how
Yeah,
they get these things?
No, I think when it was the t squared plus 4t plus 16, I wrote that as equal to t plus 4 like squared, but that is not true.
Yes, yes.
Yeah, so that equals to t squared plus 8t plus 16.
Right.
So I was yeah. So I make silly mistakes like that, but I do know how to approach it, I guess.
Mm-hmm.
Yeah, and I was wondering like why if I do that, then I get I was trying to at the end check like make sure that I get 4 roots. So
Right.
that's why. Yeah. Okay. Sorry, my dog is kind of telling me to go out. Do you mind if we kind of so tomorrow at the same time we'll go through lecture 2? Is that right? Or lecture 3?
Yeah, we're going to go through lecture 2. We've done lecture 1.
Monday lecture 3.
Yeah.
Okay. So basically the kind of the timing of this course is like Friday, Saturday. I know Saturday, Sunday, Monday.
Yeah, Saturdays are for the problem set discussions and Sunday, Monday for lectures.
Mm-hmm. Sounds good.
Yeah.
Okay.
So yeah. So tomorrow, watch the lecture 2 and we'll discuss whatever.
Sounds good.
Okay, amazing.
Yeah, this was good.
Yeah, it's very fun talking about this and like I never talked about math with other people, and even though I took calculus, I learned a lot of about random things today. So yeah. Thanks so much.
Yeah,
I really
just a
appreciate
side
it.
note before you leave, Johei, you're picking up things really fast. It's amazing to see. Do you have experience in this kind of things?
Me?
I know you.
Yeah. Or Divya? Me. I'm very old. Like I took the higher courses in calculus, theoretically, but it's just I feel like I never got the big picture. Like I guess I mean I took multivariable and linear algebra. I never was a pure math or even applied math for that matter. But but I don't know, for some reason I want to like kind of understand more than I do now instead of just like solving equations, I guess.
Right. That's actually
like I want to develop like mathematical maturity, I guess.
Right.
That's kind of
yeah.
That's where I'm going from. Like it's not to solve like some engineering problem that I have, like that I can kind of solve by computer in some sense. Like a lot of the work that I do can be done by computer without but I just want to understand more. Yeah. And I think math is like a very like beautiful like subject. Like there's like random theorems, like wow, that's whoever thought of this like is a genius kind of thing.
Right.
Yeah, and
they probably are.
Yeah, and maybe I can't do that, but like I want to kind of like know how they might have come up with such a thing. So kind of starting from scratch to on that journey. So yeah, I might be in this Discord for a while. Hopefully I can progress through like this and then multivariable and beyond that. Like, yeah.
Cool.
Hopefully up until real analysis. I think that's my goal, but it might take many years.
Yeah, that's fine.
Okay,
I'm glad that like this course and the server is being a little bit of help, in picking these things up again.
Yeah.
So this thing was recorded. It's going to be on YouTube, and anyone who missed can watch. So.
Okay. So also PSET 1 that will be due next Saturday, and that will be from the MIT problem set 1.
Right. I probably would be exactly that, or I would maybe make a bit of changes, but it would be mostly that.
Okay.
Yeah.
Sounds good.
And that will be released when we finish lecture 3.
Okay. All right. Yes. So after tomorrow.
I have not yet watched lecture 1.
You can watch lecture 1 today and maybe lecture 2 tomorrow and then join. If that's possible.
Will it
I'll probably head out
End the
now.
lecture.
Sorry.
Okay, you can.
Yeah,
Yeah, you
same.
can go.
But thank you so much.
Bye.
Bye bye.
Bye.